Okay, let's graph some arithmetic sequences. Now, a couple of things that I need to remind you about sequences. First off, a sequence looks like this, like 5, 7, 9, 11, 13, dot, 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 and that's actually an arithmetic sequence. The reason it's arithmetic, if you ever add or subtract the exact same amount to give the next dot, that's an arithmetic sequence. This is your first term, second term, third term. So another reminder is as you're plugging in values in to get this graph, you're plugging in 1, 2, 3. That's your domain. You're not going to plug in 1.5. You're not going to plug in 0. Now, I'm just going to show you first off, plugging in those values, even though this is linear. Again, I need you to know that linear, like y equals mx plus b, and arithmetic is the same thing. But I'm going to plug in some values. I'm going to find like A1, I'm going to find A2, and so on and so forth. And I'm going to graph it that way to begin with. So A1, if we plug in 1, you get 2 times 1 plus 1, which is 3. So my first term of this sequence is 3. My second term, if you plug it in, gives you a 5. My third term gives you a 7. My fourth term gives you a 9. And you can tell that it's actually a line. And we could have actually graphed it our shortcut way. It would cross right here, and then you have rise 2, run 1, rise 2, run 1. But what's different is, again, we don't plug in 0. So notice how I did an open circle. If you're going to put this dot here, make sure it's an open circle, which means it's not included as part of your graph. And here's the most important part. You don't do this. You do not connect your dots. And again, the reason why is we're plugging in 1, we're plugging in 2, we're plugging in 3. We're not plugging in anything in between, so you're done. An arithmetic sequence is finite, meaning you're not going to plug in all those values in between. Or excuse me, it's infinite, but you're still not going to plug those values in. So like here, if we want to use our shortcut, we know this thing's going to cross at 6. We know we go down 1 and we go over 2 to find other dots on my graph. But unfortunately, I'm missing some. Okay, this is what my graph's going to look like. But I've got a value at 2 and I've got a value at 4, but I don't have a value in between. So what you're going to have to do is go back and put those in between dots, which would, and you can tell where they would be. So my first term of this sequence, if you actually plugged in a 1, you'd get 5.5, which is right there. Your first value is 5.5, and then 5, and then 4.5, and then 3.5, and then 3, and so on and so forth. Okay, now we're going to actually graph geometric sequences. And if arithmetic sequences is when you add or subtract something to give you the next term, this is what geometric looks like. To where, hey, you're multiplying by 3, multiply by 3, multiply by 3, and this thing's actually increasing. It's getting bigger and bigger and bigger. So this is what an exponential, or excuse me, a geometric, now I'll use those terms interchangeable, because a geometric sequence is actually exponential. If arithmetic is linear, geometric is exponential. So those two terms are interchangeable. So what I'm going to do is I'm going to plug in, to find my first value, I'm going to plug a 1 in. 1 minus 1 is 0. Anything to the 0 power is 1. So my first term is 1.1. For my next term, I'm going to plug in 2. So, and you'll start seeing what's happening. When I plug in 2, 2 minus 1 is 1. 2 to the first power is 2. So therefore, we're doing 1.1 times 2, which is 2.2. And right now, it might look linear, but I promise it's not going to be. When you plug in your, to find your third term, when you plug in 3, you're going to have a second power. 2 times 2, or 2 to the second power is 4. So my next term is going to be 4.4, which is going to be somewhere right in there. My next term, when you plug in 4, you're going to get 2 to the third, which is 8. And my next term will be 8.8, which is going to be somewhere up there. And you see that it's got that exponential look, and that's what an exponential function looks like. But again, we're not connecting the dots. We're only plotting 0.1, 0.2, 0.3, 0.4, and so on and so forth. So that's actually, it's going to be growth. Why is it growth? Because you're pretty much just taking a number and you're multiplying it by 2 over and over and over again. Okay, the next one, you're taking a number, and in this form, that's always going to be your first number. You'll start noticing that. And you're actually multiplying by 1/4 over and over and over. So when you find your first term by plugging in, or your A1, you're going to plug in 1 for n. That's going to give you 8 times something to the 0 power, which is 1. So our first term here is going to be 8. You could find a 0 term if you wanted to, but we don't have to here, again, because we're looking for our sequence. Your second term, when you do 2 minus 1, you get 1. So we're going to do 8 times 1/4, which is going to be 2. So our second term there is 2. Then you're going to do 8 times 1/4 to the, when you plug in a 3, you're going to do 1/4 to the second. So pretty much you're doing 8 times 1/4, and then you're doing times 1/4 again. So you're going to start noticing, hey, I'm just multiplying by 1/4 over and over and over. So when you do 8 times 1/4, and then 1/4 again, let's say that's going to be 2 times a 4th, which is going to be a half. Multiply that by a 4th again, you get like an 1/8, and then you get like a 16th. And this is what's called exponential decay. That thing is getting smaller and smaller and smaller. You actually have an asymptote line there. It gets smaller and smaller, it gets closer and closer to 0, but it's never going to touch it. It just gets really close to it.